Hey everyone. Today we're going to take a look at some examples that have to do with displacement and total distance and kind of the difference between those two. This is not really a standalone lesson. We're not learning any new math here. This is just an application that we use integrals for, but this is a place where I've seen students struggle over the last couple of years, so I thought it would be helpful to pull out some individual examples so that you have them to refer back to. So we're going to start by going back to the original way we learned to talk about integrals, which is just geometric figures on a graph. And I've already calculated those areas. So if you need to pause the video and figure those out for yourself and make sure you understand where those numbers came from, please do. But really the big important thing today is that you understand the difference between these three questions, okay? So the first question says, how far did the bug end up from its initial position? This is a velocity graph, right? So I want to know, how much did the position change by? That's a displacement question. What is the net change from beginning to end? Whoops, that is a displacement. Okay. Displacement does not care about what your actual final position is. It just cares about how much it changed by. It also doesn't care about how many times you went forward and backward and then forward again. It just wants to know what's the difference between where you started and where you ended in terms of your position. And that's what an integral does, okay? So when I do a regular integral, if I was to integrate this thing from 0 all the way to 22, we would just add these areas together, right? We would say it's 12, and then we went backwards by 25 pi over 2. And then we went forward again by 32. And we could do a little bit of simplifying. Honestly, that's not the important thing here. 12 and 32 makes 44. So I could say this is 44 minus 25 pi over 2. And that would represent how much my position changed by. That doesn't mean this is my final position because I don't know what my position was at 0, right? This is just how much it changed from beginning to end. Okay, that's what displacement is getting at. And you just do a regular integral for that. Now the next question says, how far did the bug actually travel, right? If it was wearing a little bug pedometer, and it was measuring its total distance traveled, what would we find, right? And so when we're talking about total distance, because that's what this question is, total distance, we don't care about anything negative because we don't care which direction we're traveling in, right? This is still distance traveled. So the difference between total distance and displacement is total distance just makes everything positive. So we're just going to say this is 12 plus 25 pi over 2. That's really the only difference here. And then plus 32. So in my final answer, I would say 44 plus 25 pi over 2. And this, by the way, is inches per minute. So this would be measured in inches, right? That's how many inches this little bug traveled. Okay. This displacement could also be measured in inches. Okay. So the third question here is getting at what is like the final position, or maybe not even the final position, but it's asking me to find a position at x of 22. Now, we know that from 0 to 22, this is how much my position changed by, but I need to know what I started at, right? And this question also, notice, it doesn't start you at 0, it starts you at 14, right? So it's starting you here. And so we're really only looking at like this distance traveled because we're starting at 14. So at this time, at 14 minutes, I mean, my velocity is 0, but it tells me my position is 12 inches. So I must be 12 inches, I don't know, from the right edge of the picnic table or however we're measuring position in this scenario, right? So what we're going to do here is we're going to say, well, I'm starting at 12 inches. And then I know that my position increased by 32. Increased because this is positive. So I would just say I increased by 32 inches and landed at a final position of 44 inches. By the way, This 12 is not related at all to this 12. I don't know that I even knew this was going to be a 12 when I wrote this question, but this 12 is saying that I started at a position of 12 and then I added this area because that tells me how much my position changed by. So I landed at a position of 44 inches. Okay, so that's not too crazy hard when you're just looking at a graph and you're adding and subtracting areas. But when we get into doing this with functions, sometimes we don't have that visual and it's a little bit harder to do. So let's generalize a little bit. So if we're talking about displacement, displacement is just a plain old integral. And I can't remember if these are listed in your notes or not. So you may need to pause and write down the formulas. Make sure these are A's because I had a typo in my original copy. I had zeros here. So again, if they're already printed in your notebook, make sure these are A's. Okay. So displacement is the integral of a velocity function from A to B. And again, this is just measuring the change in position. It's not telling you a position, it's telling you how much your position has changed by. Okay? If you want to find what your actual position is, you need a starting position, right? You need to know at this A, wherever you're starting, what was my initial position, okay? So this is what we are eventually going to be calling an initial condition. It's just a starting value. Okay. So like here, our 12 was our initial position, and then we do the integral because that's how much we change by, right? So the integral represents change, like we said above. I'm going to run into my other stuff there. And that's what gives you your final position. Total distance, we don't need anything having to do with a position, right? We don't need that initial position there, but we do need to turn everything positive, right? And so this absolute value bracket is just saying what we did up here. We just pretended this was positive, right? That's what absolute value does. The problem becomes when you're doing this without a calculator, there's not really a way to do an antiderivative of an absolute value function. And so the math we have to do here is a little more complex. Okay, so that's what I really wanted you to be able to see, but I also want you to understand the difference between these three things. Okay, so let's flip over to the back. And this is one example where I ask you those same three questions. We are going to work through this with and without a calculator. And I'm going to start with the without a calculator because that's probably the harder one, right? And then we will verify using Desmos, okay? So we've got a velocity function, right, v of t, and it says what is the displacement of this object on the interval from 0 to 6? Okay, so we know that displacement is just a plain old integral. So I'm going to integrate from 0 to 6 the v of t function. If you wanted to copy down the function there, you could. Integrating means I need an antiderivative. So I'm going to go, let's see, my antiderivative here would be 1/3 t cubed minus, let's see, that's going to be 5 halves t squared plus 4t. Okay, that's my antiderivative. And we are going to do that from 0 to 6. Okay, I'll continue that down here because I want to save this space for when we use the calculator, right? Okay, plugging in the 6. This is not going to be super pleasant, but it'll be fine. Okay, so we're going to go, this is 6 cubed divided by 3 minus 5 times 6 squared divided by 2. I'm kind of just plugging the 6 in right now, and then we'll talk about some mental math stuff. 4 times 6 minus, now the nice thing is when I plug this 0 in, I'm going to get a whole bunch of zeros, right? Okay, so then let's see, I might pull out a scrap of paper here and show you some of my mental math trickery here. Okay, 6 cubed divided by 3. 6 times 6 times 6 divided by 3. That's what's going on there. Well, if I take one of these 6's and divide by a 3, 6 divided by 3 is 2. So I really have 2 times 6 times 6. That's 36 times 2, so that's 72. Okay, so that's how I'm doing this without a calculator. So this is 72 minus, okay, this next one, 5 times 6 times 6 divided by 2. So 5 halves times 6 squared. A couple different ways you could do this one. You could just take a 6 and divide it by 2, right? Or you could go 6 times 6 is 36, and 36 divided by 2 is 18. Either way, you're going to end up with this, 5 times 18. That's a little rough, but like it shouldn't be terrible, right? You learned this back in elementary school, and you probably thought it was a crazy way to learn how to multiply. But in your head, what I would do with this is I would say 18 is really 10 plus 8. So then I would say this is 50 plus 40, which is 90, right? So 5 times 10 and 5 times 8 is what I did there. So I got that was 90. So 72 minus 90 plus 24. And again, I don't really care about that minus 0. For this, I would probably add the 72 and the 24 first, and that's going to be 96, and 96 minus 90 is 6. Okay, so 6 feet would be what I'm getting for my displacement here. Okay, so that's just what we've been working on, right? That's the fundamental theorem. We did an antiderivative. We plugged in our 6 and our 0. And so from beginning to end, this object moved by a total of 6 feet in a positive direction. So to the right, we would say. Okay. So now let's talk about this total distance thing. And here's where we run into trouble with this. Let's see, where can I draw this? That's not going to get in my way later. If we think about this velocity function, this is a parabola of some kind, and I don't actually know for sure what it looks like, so I'm just drawing kind of a generic parabola, okay? If we're talking total distance, we can't do an absolute value with an integral. Like, we don't have a way to do an antiderivative of the absolute value of the velocity function. So what we have to do is we have to split it into pieces, kind of like that graph we did at the beginning. And so let's just say this is our parabola. I would need to find this area, right? And then I would need to find this area and make it positive. And then I would need to find, I don't know, let's say this is the 6 here. So I would need to find this area. So I have to split this into like 3 different integrals here. And in order to do that, I need to know where this is happening. I need to know where is it crossing the x-axis, okay? Those are the zeros of the function. Those are the zeros of the velocity function. So I need to find some roots here, and I have to do it without a calculator. This is where I said things get a little ugly, right? Okay, so how are we going to find roots of something like this? No calculator. Well, it's our old friend factoring, right? So this is what I'm trying to find. T squared minus 5t plus 4 equals 0. And then let's factor this, okay? And let's see, I need things that multiply to 4 and add to negative 5. So I'm thinking t minus 4 and t minus 1. And that would mean that I have roots at 4 and at 1, okay? That's where this is happening, right? These places where I'm crossing over the x-axis. So if I'm trying to get from 0 to 6, I really need to go from 0 to 1, and then from 1 to 4, and then from 4 to 6, okay? So to find my total distance, this is what I'm doing. I'm going to do an integral from 0 to 1 of v of t plus an integral from 1 to 4 of v of t plus an integral from 4 to 6 of v of t dt. And I know that looks terrible, right? But the thing with this is I have to split this up this way because any one of these pieces could be negative. By the way, I don't know for sure. I mean, I do know for sure because I understand how parabolas work, but maybe the first part is the part that's negative, right? Maybe this is the piece that's underground somehow, and then this one is positive, and then this one goes back to being negative or something like that. So any one of these could come out as a negative answer. And if it comes out negative, I just want to ignore the fact that it's negative. I just want to turn it positive. That's what absolute value does. So technically what I'm going to do is I'm going to find all these integrals, and then I'm going to say that I'm taking an absolute value of the integral itself. So whatever answers I get, I'm going to turn them all positive. That's all these bars are telling me, is that I have to take those and make them positive myself. Okay, I already did my antiderivative up here, right? So I'm not going to rewrite that part of it. I'm just going to start evaluating all of these integrals. And this can sometimes get a little gross. So here's this first one. First one is just from 0 to 1. Okay, so I'm going to start by plugging in the 1. So that would be 1/3 minus 5/2 plus 4, and then minus 0, right? Because I'm plugging in the 0 for the bottom half. That's my first integral. Sorry, this guy came out kind of slanted. Plus. Okay, now the good news is I already did the work for the 1, right? So now I have to plug the 4 in. And again, I'm looking up here at my antiderivative. So that would be 4 cubed over 3. All right, that one's going to be a little gross. Minus 5 times 4 squared over 2 plus 4 times 4 is 16. I guess I could have made this a 16 as well, but okay. Minus the 1, right? And the 1 we already know is 1/3 minus 5/2 plus 4. Because we did that over here. Okay. Plus, okay, let's go down here. Well, I'm trying to think. Yeah, this should be okay. Now I'm plugging in the 6. Now, we already have our answer for the 6, right? When we plugged the 6 in up here, because this was a minus 0, we just got an answer of 6. So let's work smarter, not harder. When I plug the 6 into my antiderivative, and actually knowing that, well, no. I was going to say maybe I can fit it in here, but I still need the 4. So there's the 6 minus, now let's plug the 4 in. So 4 cubed over 3 minus 5 times 16 over 2 plus 16. And again, that is just the same as this. Okay, we're going to need some common denominators here. Okay, but take this one little piece at a time. All right, don't panic. 1/3 and 5 squared, we need a common denominator here probably of 6. So I'm going to say that this is 2/6 minus, multiply this by 3, so 15 over 6. And then let's make this 24 over 6. And I'm not worried about the minus 0, right? So that's this, that's this, that's this. Okay? Plus. Okay. Here, I'm seeing 4 cubed is 64, right? So 64 over 3, but then I'm subtracting 1 over 3. So I'm doing 64 over 3 minus 1 over 3, which gives me 63 over 3. And I guess let me write it that way. But this is going to work out pretty nicely here in a second. 63 over 3. Okay. Now here, 16, this is 16 over 2 is 8, right? And 8 times 5 is 40. So I guess I'll just put down a 40 plus the 16. And then over here, what have I not included yet? I already did the 1/3. So I need a minus 5/2. Oh, and then this negative sign needs to distribute. So this is actually a plus 5/2 and then a minus 4. Okay, we'll crunch those numbers in a minute. plus. Okay, now over here I might be out of luck. Here I end up with 6 minus 64 over 3 minus, we already figured out this is 40. And again, this negative sign is distributing, so this would actually be a plus 40 and a minus 16. Notice I'm not combining anything like outside of those absolute value bars. I can't combine this stuff with this stuff, okay? Because I have to do that absolute value piece. Okay, so let's see. Over here, I've got all common denominators. So 2 minus 15 is negative 13. Negative 13 plus 24 gives me 11 over 6. Okay, 63 over 3 is 21, right? Because you can divide both of those by 3. So 21 plus 16 is 37. Minus 4 would be 33. Minus 40 would be negative 7. And then negative 7 plus 2.5 is what that is. So negative 7 plus 2.5 would be negative 4.5. Okay. And notice that one came out negative, so that's why those absolute value bars are important. That also makes sense with our picture that we drew here, right? Now for this one, ooh, that's going to get kind of ugly. I guess I can make some common denominators here, right? I could put everything over 3. So I could make this an 18 over 3 minus 64 over 3. This would be 120 over 3. And 3 times 16 is 48, so 48 over 3. And then, oh, let's see. I'm going to start with the 120 and the 18. So that's 138. Minus 48 would be 90, and then 90 minus 64 would be 26 over 3. Oops. Okay, and maybe I'll take this 4.5 and make it a 9 over 2 so we can do some common denominators here. And then I've got a 6, a 2, and a 3. Let's make them all 6s, right? So let's make this 11 over 6. This is going to turn positive because of that absolute value, and I'm going to multiply by 3. So that would be 27 over 6. And then this one I'm going to double, so that would be 52 over 6. 52 and 27, that's 79, 89. So I think we get 90 over 6 as a final answer. Okay, we will check that with a calculator in a minute. This is way easier without a calculator, okay? Way harder without a calculator. But that's what we would go from there. Okay, now on this next piece, we're going to work smarter, not harder again.